Hello and welcome everybody. My name is Elliot, and in this physics mini lesson, I'm going to show you the principle of least action for a particle in Einstein's theory of special relativity. In my last video, I taught you about the principle of least action for a particle in Newtonian mechanics, which says that of all the paths that a particle could take in getting from point A to point B, the one that it actually chooses is the path that minimizes this number that we called the action. The action that we wrote down last time was the integral along the path of the kinetic energy minus the potential energy. That seemed like a sort of random definition, but we saw that by minimizing that quantity, we indeed reproduced the expected equation of motion. Now we want to see if we can apply the same framework in special relativity, which describes the physics of things that are moving very, very quickly. Quickly meaning at a significant fraction of the speed of light. If you've studied any special relativity before, then you know that things get weird when objects start moving close to the speed of light. We'll see that we can describe the mechanics of a relativistic particle using the principle of least action, but we need to write down a new formula for the action in order to do it. As a matter of fact, we'll see that the relativistic action actually looks a lot more natural than the Newtonian action. It'll be geometric, in fact. As time goes by and as the particle moves around, it traces out a curve in space-time that's called the world line of the particle. And the action will essentially just be equal to the length of the world line. So that in getting from point A to point B, the particle is just going to pick the straightest and shortest path that it can, with a couple of caveats that we'll get to. Where things get really interesting is in Einstein's theory of gravity, general relativity. According to Einstein, a massive object like a star warps the space-time around it, transforming it from the flat space-time of special relativity into a curved space-time. Then we have to ask ourselves what it even means for a particle's path to be a straight line inside a curved space. I'll tell you a little bit more about that in a future video, where I'll show you that by demanding the principle of least action for a particle in general relativity, the particle has to follow a very special kind of path called a geodesic. But that's for next time. You can subscribe to the channel if you want to stay tuned and learn more about that. For this video, we're going to talk about a particle in special relativity. If you've learned some special relativity before, that's great. But even if you haven't, I hope you'll still get something out of this video. It just might seem a little bit mysterious at times. But to be honest, relativity really never stops feeling mysterious, so at least you're in good company. Let's start with a 60-second review of what we covered last time. We had a particle of mass m traveling from point 1 to point 2, and we wanted to find the trajectory x of t that it's going to follow in between. From Newton's second law, the trajectory is going to obey the equation of motion, mx double dot equals minus du by dx, where x double dot is the acceleration and u is the potential energy. That's one way of getting at the equation of motion. The principle of least action gives us another way. We define the Lagrangian L as the difference between the kinetic energy and the potential energy. And then the action S is the integral of the Lagrangian over time. S is a number that we can compute for any path that connects point 1 to point 2. And what we showed is that of all those possible paths, the one the particle actually follows is the path that minimizes the action. Now, that discussion was limited to Newtonian mechanics. In other words, we were assuming that the particle wasn't moving anywhere close to the speed of light, c, which is about 3 times 10 to the 8 meters per second. One of Einstein's first great discoveries early in his career was that physics looks radically different when things start approaching the speed of light. But the principle of least action is not limited to Newtonian mechanics. It extends just as well to relativistic speeds. It's just that we need to replace this particular action that we wrote down with one that's appropriate for a relativistic particle. I want to explain the fundamental idea here without things getting overly complicated. So I'm going to assume we have a free particle, meaning a particle with no forces that are acting on it. Essentially, that means setting the potential u equal to 0. A free particle travels along a straight line, because there aren't any forces pushing or pulling it in one direction or another. In space, a straight line between two given points is of course the route that minimizes the distance between them. In space-time, a straight trajectory between two events maximizes what's called the proper time. And that's going to be the key insight for writing down the relativistic action. So let me break down what that means. Let's first review some basic geometry. It might seem like I'm being a little pedantic here, but things are going to get weird in a moment when we start talking relativity. And so it's a good idea to refresh our memories about some fundamentals. Think about the xy plane. Say we have 2 points that are separated by a distance delta x in the x direction and delta y in the y direction. Then Pythagoras taught us how to find the distance delta s between the 2 points. It's given by delta s squared equals delta x squared plus delta y squared. If we let the 2 points get really close together so that the distance between them becomes infinitesimal, we usually indicate that by replacing these deltas with d's. So ds squared equals dx squared plus dy squared. This expression defines what's called the metric of the xy plane, which is just a fancy way of saying that it tells us how to measure distances. If we have some curve y of x, then we can use the metric to measure its length by breaking the curve up into lots of little line segments, each of length ds. Then if we want to know the total length of the curve, we just integrate over all these little pieces. To write that as a more familiar integral, let's grab this factor of dx squared from inside the square root and pull it out front. Then we get the integral of dx times 1 plus y prime squared square root. You may have learned this formula before in your calculus class, and I used it in a video a couple of weeks ago when I showed you how to find the shape of a hanging rope. Alright, that was the geometry I wanted to review. Now let's get back to relativity. Let's say we have a particle that's sitting at position x and at time t at a particular moment. Those 2 coordinates define a point in space-time, which we call an event. As the particle moves around and as time goes by, this space-time point is changing. And if we connect up all the events through the particle's life, we get what's called its world line, the path that the particle takes through space-time. I'm focusing on the t and x coordinates here for simplicity, but of course we can also throw in the y and z coordinates as well. Now, for whatever reason, when drawing pictures like this in space-time, it's conventional to draw time flowing up on the vertical axis and space on the horizontal axis. Notice that even if a particle happens to be sitting still in space, it's still moving forward in time. So the world line of a particle that's just sitting still is a straight vertical line pointing straight up. I'm also going to throw in a factor of c on the vertical axis here, so that it has the same units of distance as the horizontal axis. That has the nice feature that in this picture a ray of light traveling at speed c will have slope 1. And since a massive particle can never go any faster than the speed of light, the slope of its world line can never dip below 45 degrees. The claim is that the relativistic action is simply going to be given by the length of the particle's world line, up to some constant factors. So how do we find the length of a world line? This is where things start to get tricky. Space-time is not like regular old space plus an extra t coordinate tacked on. Mathematically, a lot of the bizarre relativistic physics that Einstein and Lorentz and Minkowski and others discovered comes from the fact that distances in space-time are measured by the following metric: ds squared equals minus c squared dt squared plus dx squared, what we nowadays call the Minkowski metric. Yes, that's a minus sign in front of the time term, and that's what makes the geometry of space-time so different and so confusing compared to what we're all much more intuitively familiar with. If you've learned some special relativity before, you may recognize this expression as the invariant interval between 2 space-time events. If not, for now you'll just have to take my word for it, that this is how distances are measured in space-time. With the metric in hand, we can write down the length of a world line through space-time, again by slicing it up into lots of little segments and integrating. But that minus sign immediately starts making things awkward, even in the simplest case where our particle is just sitting at rest in space, and so the world line is a straight vertical line. In that case, dx is equal to 0, and so ds squared is simply minus c squared dt squared. But that's a negative number. In fact, that's always going to be the case along the world line of a massive particle. The reason is that the speed of the particle, dx by dt, has got to be less than the speed of light, c. Then if we square both sides, we learn that dx squared is less than c squared dt squared. And therefore minus c squared dt squared plus dx squared is negative. So ds squared is indeed going to be negative, and that makes taking the square root a little bit awkward. So let's instead agree to flip the sign before we take the square root. Then the square root of minus ds squared is the square root of c squared dt squared minus dx squared. Now we can define the length of the world line just like we did in the xy plane by integrating. It's going to be convenient to pull out this factor of c squared dt squared from inside the square root. Then we can write this as c times the integral over time of the square root of 1 minus x dot squared over c squared, where x dot is the velocity of the particle. This integral on the right-hand side is called the proper time along the world line. Physically, the proper time is what would show up on a wristwatch that you strap to the particle as it moves around through space-time. For the particle that's just sitting still at rest in space, x dot is equal to 0. And so the integral that we get for the proper time is just t2 minus t1, the time interval between the events in this lab frame that we've set up. But for a particle that's moving around on its way between the two events, x dot is going to be non-zero. And so we're going to get a different answer for that particle's proper time. The key thing to notice here is that this square root, which appears in the integral, is always going to be less than 1. Again, that's just because the speed of the particle has to be less than the speed of light. So the time that ticks off on the moving particle's watch is less than the time on the stationary particle's watch. This is called time dilation, and it's probably the most famous of all the weird effects that we see in special relativity. What we've been talking about here is basically the setting for the famous twin paradox, where you sit still on Earth while your identical twin flies off around space in a rocket ship for a little while before coming back to Earth. More proper time will have elapsed on your watch and less on your twin's watch. And we're not talking about semantics here. When you reunite, your twin will be younger than you, like Matthew McConaughey at the end of Interstellar, potentially by a lot if they were gone long enough and traveled at a significant fraction of the speed of light. I might make another video all about the twin paradox at some point in the future. But for now, the thing I wanted you to notice is that the proper time between two events, in other words, the length of the world line, is biggest for the straight line trajectory going between them. In regular old space, of course, a line is the shortest distance between 2 points. What we've learned is that in space-time, because of that minus sign in the Minkowski metric, a straight line between two events maximizes the proper time. Which brings us back to the principle of least action. A free particle going between two events travels along a straight trajectory in spacetime. And so what we've learned is that of all the paths that the particle might have taken, the one it follows is the path that maximizes the proper time. So we should choose our action to be proportional to the length of the world line. And that's basically right. There's just two things we need to fix here. First of all, the units. The action is supposed to have units of energy times time. And so we need to multiply this by m and c. Also, we typically want the action to be minimized. That's why we call it the principle of least action after all. So we'll add a minus sign to make the action minus the length of the world line instead. This is the action for a free particle in special relativity. In fact, it's also the appropriate action in general relativity, Einstein's theory of gravity, except that in that case, the Minkowski metric of flat spacetime is replaced by the curved metric of a spacetime that's been warped by the presence of a massive object like a star. I hope to tell you a little bit more about that in a future video. In either case, the action is just about as simple as it could be. It just measures the length of the particle's world line through space-time, and so the particle follows the path that extremizes this length. Okay, there are two more things that I want to show you for right now. First, to take the variation of this action and actually shows that it gives us the expected equation of motion. And second, to show that it's consistent with the Newtonian action that we wrote down before when the particle is moving slowly compared to the speed of light. Expanding things out, remember that minus ds squared was c squared dt squared minus dx squared. I'm going to pull out this factor of c squared dt squared from inside the integrand again. So we can write the action as minus mc squared times the integral over time of the square root of 1 minus x dot squared over c squared. Like we learned last time, to apply the principle of least action, we take a small variation of the path. X of t goes to x of t plus epsilon of t. Then we demand that the action stays the same at leading order in epsilon. In practice, this just means taking the derivative, or really the differential of the Lagrangian. Here's our Lagrangian in this case. when you make a tiny change in x, the resulting change in L is minus mc squared, and then we take the derivative of this square root. That gives us 1 over the same square root times a factor of half. Then we take the derivative of the thing that was inside the square root. That's minus 2 times x dot over c squared. And finally, we multiply it by the change in x dot, which is d epsilon by dt. We can cancel out these minus signs, these factors of 2 and c squared. And also, this factor of 1 over this square root here, that shows up so often in relativity that we usually denote it for short by gamma. Then the change in the action, ds, is given by the integral of the change in the Lagrangian. And remember from last time, we used this trick of integrating by parts to move this time derivative off of the epsilon and onto the rest. That gives us a minus sign. We have epsilon, and then times d by dt of gamma mx dot. Since this is supposed to be 0 for any function epsilon, we conclude that the thing it multiplies here has got to vanish independently. That's the equation of motion. D by dt of gamma mx dot equals 0. In Newtonian mechanics, the analogous calculation would have given us Newton's second law. D by dt of the momentum mx dot equals 0. In words, a free particle travels along in a straight line with constant momentum. For a relativistic particle, what we've discovered here is that the relativistic momentum gets another factor of gamma multiplied to it. And so a free particle travels along a straight line with constant relativistic momentum, gamma mx dot. When x dot is small compared to the speed of light, like for everyday objects that are well described by Newtonian mechanics, then this gamma factor is very close to 1. And so the relativistic momentum reproduces the more familiar expression at everyday speeds. Along those same lines, the last thing I want to do is show you that our relativistic action reproduces the Newtonian action we wrote down before when x dot is small. To do that, we'll use the following approximation for the square root of 1 plus a tiny number epsilon. It's approximately equal to 1 plus epsilon over 2. That's just the Taylor series for this function expanded around epsilon equals 0. And in this case, I want to apply this approximation with epsilon equals to minus x dot squared over c squared. That way, we can replace the square root that shows up in the Lagrangian with 1 minus 1/2 x dot squared over c squared. Now we'll multiply in this factor of minus mc squared, cancel some things out, and we wind up with the Lagrangian equals 1/2 m x dot squared minus mc squared. This second term here, that's a constant, which doesn't matter when you add it to the Lagrangian. It's not going to change the equations of motion because it doesn't change where the action is minimized. The first term, meanwhile, is the kinetic energy in Newtonian mechanics. So we've indeed reproduced the action for a free particle in Newtonian mechanics by taking the limit of our more precise relativistic action when x dot is small compared to the speed of light. So we've written down the action for a free particle in special relativity. It's just equal to the length of the world line that the particle traces out as it moves through space-time. The particle essentially chooses the straightest and shortest path that it can in getting from event A to event B. More precisely, it takes the path that maximizes the proper time. Einstein's special theory of relativity tells us about how to do physics for particles that are traveling close to the speed of light. But about 10 years after publishing his special theory of relativity, Einstein generalized his work to include the effects of gravity. And we call that theory, well, general relativity. The basic idea is that the presence of a massive object like a star dramatically warps the space-time around it. Then the flat Minkowski space-time metric that we worked with here is replaced with a curved metric that describes this warped space-time. But the same action principle that we discussed here will still hold in general relativity. It's just that we need to use the new curved metric when we compute the length of the particle's world line. Remember, it's the metric that tells us in the first place how to compute distances. And so, by warping the metric, the star changes what we're going to get for the length of the world line. Then the particle still follows the straightest and shortest path through space-time that it can. But in a curved space, we need to generalize our notion of what it even means to be a straight line. The resulting shape is called a geodesic. I'll share another video with you soon explaining a little bit more about how all that works. So please subscribe to the channel if you're interested in seeing that. I'll also put a link down in the description to the notes that I wrote up to go along with this video. You can check those out if you're interested in exploring all this in a little more detail. Otherwise, that's it for this video. Thanks for watching, and I'll see you next time.